All right. I'm going to record to this computer and you should be able to share now.
Okie dokie. Let me check. And everything's all set up on Zoom?
Yeah.
Perfect. Can you guys see my screen?
Yes.
Yes.
Yes. Yes.
Wonderful.
Let's see your face.
Okay. Alrighty. Jim, am I clear to begin?
Yes, you are.
Wonderful. All right. Hello, everybody. I'm Christina. I'm a research professional with the University of Minnesota, Minnesota Institute for Astrophysics, and I will be presenting on the eyes, ears, and telescopes. So chasing cosmic clues with Kilonova Catcher. Kilonova Catcher is a citizen science project that anyone can join. It is dedicated to the discovery of the optical counterparts to gravitational waves and other fast transients. And don't worry, I will be explaining what all these phrases mean, especially if some of them are foreign to you. So a little introduction to Kilonova Catcher. We are a community of amateur astronomers. So we have 189 registered users in all continents, 159 individual telescopes, and 14 remote telescopes. We perform live follow-up observations of the optical counterparts to gravitational waves and other fast transients. And our members collaborate with scientists and contribute to the field of multi-messenger astronomy, interacting across the world. And it is a wonderful community of individuals of different cultures and countries all coming together to communicate and even help refine and develop resources for Kilonova Catcher and for its new members. But what is this field that Jim introduced and then I restated? What is multi-messenger astronomy? And so you can think of multi-messenger astronomy as another way for scientists to gain information from the universe. And so how do astronomers observe things or see things at a distance? We have a variety of different telescopes or detectors. And so we have electromagnetic radiation, light, which is your traditional telescope, your Hubble, your Vera Rubin. They see visible light, UGRIZ for our astronomers and scientists. We have neutrino detection, which detects particles. We have gravitational wave interferometers, which you could consider observatories, but there's a whole debate about the vocabulary there. And then there's cosmic ray detectors, which are similar to neutrino detectors. And so multi-messenger, I keep saying that, multi-messenger. And so you can kind of correlate multi-messenger astronomy to how humans detect things at a distance. So we have our eyes, which are designed to detect light. We have our ears, which are designed to detect a different type of wave, sound waves, compound waves that require a medium to travel through. We have smell, which is designed to detect particles, kind of like neutrino detectors. So we have our eyes like telescopes. We have our ears like gravitational wave interferometers. And we have our sense of smell, which detects particles, like our neutrino detectors. You notice there's no sense of taste here. That's because the only scientists that taste anything are geologists. They like to lick rocks. That is scientific fact. All right. And so you can notice that these detectors look absolutely nothing like each other, both in science and within humans. And so multi-messenger astronomy is the study of astrophysical phenomena through different types of cosmic messengers. Our eyes to the universe, electromagnetic radiation, our ears to the universe, gravitational waves, and our nose to the universe, neutrino detection and cosmic rays. And so now we're getting into our namesake, kilonova and gravitational waves, our eyes and ears to the universe. And so here is a general consensus of our general process of what the relationship between gravitational wave detection, which are waves, they're not sound waves, but they're waves that require a medium, the universe. All right, so we get a gravitational wave detection alert. We then look for optical counterparts, so through with visible light. We also look for other signals at the same time to kind of say, hey, this actually is a gravitational wave optical counterpart. We look for the binary neutron star merger, the short gamma ray burst, both optical, or other messengers. So what are gravitational waves? So like I said before, you can think of gravitational waves um, as I used a metaphor, which is the sound wave, which is, energy traveling through a medium. It's a wave. However, Gravitational waves occur when two super dense objects merge or collide into each other. So this collision releases such power that it perturbs the universe itself. Gravitational waves, according to Einstein, consist of the oscillatory space warp, this stretch and squeeze of space as this energy propagates through it. So that's the whole universe stretching at one point, squeezing in another, changing its diameter as this energy flows through it. How do we detect gravitational waves? We use detectors called interferometers, and you could consider them observatories. These observatories use mirrors spaced several kilometers apart to detect tiny vibrations from passing waves, gravitational waves, or the oscillations in the diameter of our universe, just as a reminder. These detectors are capable of sensing a change of less than 1/10,000th the charge diameter of a proton. That is incredibly small, incredibly sensitive detectors. And currently, we have three functioning locations. So LIGO, Virgo, and CAGRA. And so LIGO is in the United States. There is one in Louisiana and in Washington. There is Virgo, which is in Western Europe, and there's CAGRA in Japan. There's also one in discussion to be developed in India. And then we also have a space interferometer that's being designed called LISA. So here's an explanation of how interferometers work, how they detect that the universe's diameter has changed.
To measure this stretching and squeezing, Ray turned to a device called an interferometer. A laser beam is split and sent down a pair of long perpendicular tubes, each precisely the same length. The two beams bounce off mirrors and recombine back at the base. The light waves come back lined up in such a way that they cancel each other out.
You add them together, you get nothing. You get a zero, a big fat zero. No light gets detected at the photodetector.
But when a gravity wave comes along, it distorts space and changes the distance between the mirrors. One arm becomes a little longer, the other a little shorter. An instant later, they switch. This back and forth stretching and squeezing happens over and over until the wave has passed. As the distances change, so does the alignment between the peaks and valleys of the two returning light waves, and the light waves no longer cancel each other out when added together in the recombined beam. Now some light does reach the detector, with an intensity that varies as the distance between the mirrors varies. Measure that intensity, and you're measuring gravity waves.
The light takes longer time in here than it did in this arm. Now it takes a shorter time, and these things don't cancel so beautifully anymore.
Right. So that is how gravitational wave interferometers work. And to kind of bring everything together about gravitational waves, when thinking about gravitational waves, a question you can ask yourself is, to what extent does one event interact with the rest of the universe? That is what gravitational waves are. So when two extremely dense objects merge, all right, all of these particles want to be in one spot and they can't, and they're fighting against each other. And all of them throw a tantrum at one time, and it just sends this shock wave out. And that shockwave propagates throughout the whole universe. It perturbs the universe to such an extent that billions of light years away, we can detect these gravitational waves. We can detect them, usually gravitational waves are sensed to 100 megaparsecs. 100 to 1,000, sometimes even farther megaparsecs away, incredibly far distances. So how do gravitational waves interact with the universe? So what is their physics? So gravitational waves travel the speed of light, the limit of travel speed in the universe. They propagate in all directions. However, the strength and the polarization, so depend on the viewing angles. And so basically what that means is that the confidence in our, hey, this is what we're looking at, or hey, this is what caused this gravitational wave, depends on the viewing angle. So what angle did this collision occur in that the gravitational wave is propagating towards us at? And so how do gravitational waves interact with mass and gravity? So just like light, gravitational waves can be lensed by massive objects, just like bending around a galaxy, just like light bending around a galaxy. All right. So how do gravitational waves function over time? So gravitational waves do not function under the inverse square law like gravity or light. They decrease much more slowly as a function of their distance. So how can we observe gravitational waves? So we're a bunch of telescopes. Gravitational waves propagate through the universe. How can we observe them? This is where kilonova come in. All right. Not to be mistaken for supernova, kilonova are powerful transient astronomical events. And I keep saying that, transient. Transient means that these phenomena evolve. The light evolves. It goes up, it comes down at a very specific rate. Kilonova are, yeah, please. Kilonova are incredibly dense objects made up of entirely of neutrons. Um, Kilonova occur when two neutron stars or a neutron star and a black hole, or two black holes with matter around it, combine and there's an explosion. Right? They occur in compact binary systems. And so compact binary systems are when there are two objects, whether it's like I said before, and kilonova or neutron stars, if there's one in the system, neutron stars stem from large stars that have collapsed in on itself. And so when the outward pressure, ooh, I do have, yes, right here. I'll go back one. When the outward pressure can no longer compensate for, so the outward energy generation of a star can no longer compensate for the weight of the star itself at its current size, it all collapses in on each other. Everything wants to be in one spot at once. It can't. The neutrons, electrons, all the particles within the atoms of a star collapse together. They neutralize each other, and then it's just a star made up of neutrons. And so this is why kilonova are such powerful objects, why they generate gravitational waves. So they form, like I said, the neutron star is the collapsed core of a supergiant star. They form when a massive supergiant runs out of fuel and it leaves this high density core behind. And neutron stars are the smallest and densest currently known class of stellar objects. And when we do have a kilonova, when we do have this system merging, so two neutron stars, a neutron star and a black hole, more specifically, they generate gravitational waves with very unique waveform evolution. Neutron stars merging will have much higher peak frequencies, but B and S mergers have the largest because there's more mass involved. Okay, so how do we get information from gravitational waves? So when we get a gravitational wave signal, when we see this plot and it's a wave, right? And we see this weird curve on it, and that's what's called a chirp, right? And each of the progenitors of gravitational waves have a unique curve to them, a unique wave, right? Binary neutron star mergers have higher frequency gravitational waves, a few kilohertz. They have a long duration chirp lasting up to a minute. So that's a minute of this chirp, this sound. They have a weaker amplitude and due to lower total mass. Because while binary neutron stars have, while binary neutron stars are quite powerful, they're much more visible than black holes merging. They don't have as much mass because, again, they're the condensed core of a star, of a dead star. You have binary black hole mergers. So this has a low frequency gravitational wave, 10 to 100 hertz. They have a short and strong chirp lasting just a few seconds. And they have a strong amplitude because of the high total mass. Because black holes, despite not being visible or producing light, have much more mass than neutron stars. And so neutron star black hole mergers are a combination of the two. They have mixed frequency characteristics. They can be much harder to distinguish. It depends on the mass ratio. Was this a small black hole, a large black hole, corresponding to the neutron star? Because there is some variation of the size of neutron stars. Sometimes they can resemble a binary black hole if the neutron star is completely swallowed, or if it's disrupted. So the signal, it leaves a distinct signal due to tidal effects if the whole thing is just kind of like torn apart, which can happen. And there's a lot of science behind that. There's a lot of machine learning algorithms in development to distinguish between binary black holes with a lot of matter around them and a neutron star black hole merging with or without a kilonova attached to it. And a kilonova is the bright flash that occurs when these two things merge. So why do we want to study kilonova? What is the significance? Well, it helps us understand how matter behaves in superdense environments. And remember, we can't study the beyond the event horizon of a black hole in the singularity, but we can see what happens in extremely dense environments like neutron stars. Again, neutron stars are the one of the densest known objects in the universe. Kilonova produces heavy elements like gold and platinum. And these are also very faint and fast fading, very rare cosmic events. So we want to really focus on what we're seeing when we see it. And that's why Kilonova Catcher is so important, because it's a group that can be triggered as soon as we get these alerts. All right. So what does a kilonova look like? What does observational follow-up look like? And so on August 8th, 2017, there are scientists sitting at LVK monitors waiting. There are, graduate students, professors, postdocs, just, this launched in 2015. It's the second operating run. People are waiting to see something unique, not just noise, not just another binary black hole merger, which occurred in 2015. We want to see a optical light source to a gravitational wave, and it hasn't happened in 2 years since gravitational wave detectors went live. So on August 8th, 2017, everybody's sitting around waiting, monitoring, because being an astronomer means you're kind of sitting around looking up at the stars a lot. Go figure. When there's a chirp, and this chirp goes on for a minute, and a lot of people who are waiting there are just like, oh, that's nothing. It's really no big deal. Until, within a few minutes, people start getting alerts from the Global Coordinates Network. Like, hey, uh, we're seeing something around the same area that you guys got a gravitational wave a few minutes ago. What's going on? Why didn't you send an alert out? They thought it was noise. They thought it was nothing. They thought that somebody walked too close, a tree fell over, a raccoon yelled somewhere nearby. They thought it was nothing. Until they went back and looked at it again when everybody else was starting to see something, when the telescopes were starting to see something right nearby. And so all of a sudden, everybody is looking in this direction into this gravitational wave detection. And they're like, oh, this is a neutron star merger. And so GW 170817 is so significant because it was the first time that a gravitational wave detection was confirmed by non-gravitational means, which means it was the first neutron star, the first optical collision that was detected. The aftermath of this made careers for everybody who was in multi-messenger astronomy at that time. This merger was seen by 70 observatories on 7 continents and in space across the entire electromagnetic spectrum, marking a significant breakthrough for multi-messenger astronomy. It also proved that short gamma ray bursts are often, almost exclusively associated with kilonova, with neutron star mergers, because 1.7 seconds after the GW merger signal went out, Fermi and Integral, which are spacecrafts, detected a short gamma ray burst. And so what are short gamma ray bursts and what are GRB afterglows? And so gamma ray bursts are brief, intense flashes of gamma rays and X-rays that occur in distant galaxies. And the significance of GW 170817 was not only that it was once refined, it had a good signal to noise ratio, but that it was so close. It was 40 megaparsecs away. And to be honest, we don't want these events to be any closer. Maybe the neighboring galaxy, because of how powerful gamma rays are. By the time we even realized we were seeing anything, we'd have been gone 5 minutes ago. That's how strong gamma ray bursts are. So when a gamma ray burst occurs right after the kilonova, this bright flash when the two neutron stars merge, it superheats all the gas in the area. And kilonova are faint and fast fading. So they rises at 1 magnitude per day and fades at 0.3 magnitudes per day. This means that you have hours, days, maybe a week to observe a kilonova before it's gone. You have moments to respond to a kilonova alert and you've already lost data. That's how fast these things evolve. And so the significance of finding a GRB afterglow is that the shock, the energy from the gamma ray burst from the afterglow leaves an ember for us to observe and gather more information over time. Even after the kilonova phase, the GRB afterglow will still be there. So where does Kilonova Catcher come into play? K and C. So we have two scientific programs. So we have our core program, which is binary neutron star mergers and their optical counterparts, such as gamma ray bursts, kilonova of different kinds. And we also do long gamma ray burst follow-up and supernova as well. And so we not only look for all the optical counterparts of gravitational waves, so neutrino detection, short gamma ray bursts, kilonova, obviously, but we also look at other different forms of transients like gamma ray bursts and supernova because it helps train our members. It also helps to be able to better understand the telescopes within our system because Kilonova Catcher is unique because even though it's a citizen science program, we do expect science quality images. And a lot of our members are have trained each other, have educated and learned with one another alongside scientists to be able to provide these. And so what is expected of what is needed to be inside this collaboration to function well within it? And so we require a minimum diameter of 20 centimeters, about 8 inches. We use Johnson BVRI, SDSS GRI, and luminance unfiltered filters or clear filters. We have a distribution of telescope aperture sizes. So as long as you can reach certain magnitudes with stacked images, you can observe with us. So in G, we reach magnitudes as low as 21.5, in R, 21, and I, 17.8. And for anybody who is new or just needs a reminder, the higher a number is, the dimmer it is, the lower a number is, the brighter it is. It's part of a log scale. It's really, really old. I think like 2,000 years old, because we don't like to leave the Grecians behind. You know, they did found a lot of this, but so as long as a telescope that you have can reach these magnitudes, you can observe with us. So how does it work? So to kind of review a lot of the theory, all in one point, we have a gravitational wave alert. And then we're like, okay, this gravitational wave alert provides a map. And on this map, you know, there's a lot of different points somebody can look at. And obviously you can't look at all these spots at one point. And so we'll start observing one point called tiling or galaxy targeting, and we'll wait for observatories with larger field of views or for a neutrino detection, because when we have a neutron star merger, there's usually a neutrino detection that can pinpoint stuff with greater accuracy that comes alongside it. And so as soon as we get that, we're like, hey, everybody, I need you to go look at these coordinates because there's a neutrino detection within this map that we're looking at that the gravitational wave interferometers provided. And so as people start detecting the GRB afterglow, the neutrino detection, we start narrowing down into this center point. But how does all that information get translated from the professional scientists at GRAMA? Because GRAMA is the Global Rapid Advanced Network dedicated to multi-messenger astronomers. Grandma, the scientists with Grandma will say, okay, we're getting all this information. We've gotten this alert. We've gotten that alert. Let's now start triggering our observatories. And Kilonova Catcher is considered one of Grandma's observatories because it's a team of telescopes, a team of amateur astronomers who can follow up with us. So we have the Kilonova Catcher website, which will, as soon as there's an event, it creates a event input where you can upload, where you can get your observation plan. So it tells you where to look and when to look. You get coordinates. You have a campaign deadline. So, hey, you have 36 hours to observe until we stop observing, because usually if you haven't detected it by that time, you're not going to. And it's a place where you can upload your images and be communicated with. We also send emails with the coordinates and updated information. And we also have alerts that occur in Skype, that occur in Slack. And we have an astronomer guide that explains how do you send images. And so we do it a few different ways. You can upload them directly to Kilonova Catcher's website, which will take your raw images, compile them, and help you put a header on them, which is kind of like, oh, we did this, and it was at this location and these coordinates. It's the density of information that's needed to make scientific images. And so you can upload that using the Kilonova Catcher website. And if you have other photometry tools, if you are a experienced astronomer, you can just send them directly to us, either via email or OwnCloud. I get emails at all time of the night because people are observing all over the world. It's a lot of fun. And here is a poster. Jim, I'll send you this presentation afterwards. I do believe you still have this poster when we first started talking together. Jim was a individual I met through SciStarter, so this is how I got to present with you guys. And so I presented this at the NASA conference, introducing Kilonova Catcher to be a NASA partner. And so this poster will explain how we go from event detection to processing it through Sky Portal to KNC getting alerts, how we coordinate with telescopes, the KNC website, and then what is done with these images. So this is where we're getting to. How do we go from taking an image with a telescope to getting science out of it? And so the scientists on the grandma side have a program that'll process these images and we'll get data from it. We'll get a magnitude and we'll get a date. And so we'll be able to plot that information over time. And so we'll be able to see the light curve, as you can see here. I do have a larger version of this later on in the presentation. And in order to be able to get science quality images, members of the Kilonova Catcher team, including myself and scientists, have come together, so all of us working together, scientists and amateur alike, to write a manual for both newcomers and people who want to become more proficient with true astrophotography, true science-taking images, science quality images. And so you can learn the science. So what is a kilonova? What is needed to take an image? How deep should you observe? Master the tools of the trade so you can get hands-on with astrophotography basics, learning what a bias, a dark, a flat is. And this is a manual that we all wrote together. It teaches you how to turn raw data into discovery, into science-worthy images, how to use real observing software. And our community is so happy to have new people in that we work together consistently to make sure that everybody knows what to do, how to respond, because these events happen so quickly. These targets are triggered randomly at a moment's notice, and we need to respond. And so at the end of the day, at the end of the month, at the end of the year, what happens to all this data? So we're observing, once, twice a week. We get a GRB alert. We get a short GRB alert about once or twice a month. We get kilonova detections, a little bit less than that. So what happens at the end of it? Well, we publish. We publish scientific papers. We publish to the Global Coordinates Network, or the NASA's GCN, which is basically a forum to trade information about events that are being observed. And so Kilonova Catcher, your names, amateur astronomers' names, are published in real life, in real time, consistently. It is never without credit. And just this year alone, we've had five GCNs or more with Kilonova Catcher's name on it. We had over a dozen last year. And we've also had 3 papers this month, as well as you can see the skill of our amateur astronomers. Some of these people have been, amateur astronomers for decades. Some of them have just started. And they are amazingly talented individuals. And even when I came into this, because I am an astrophysicist, I do a lot of programming on very, very large telescopes, and I'm actually programming the metrics to detect fast transients with the largest observatory on the planet currently, the Vera C. Rubin. But when I came in, I didn't know how small telescopes worked to a certain degree. And so I asked them, and they were more than happy to reciprocate and provide information. And we have a social media page, we have a social media following, and I post the images that occur from different observations onto this Instagram page and on various social media, just to kind of show off, like, hey, Kilonova is doing some pretty cool stuff. Like this picture here and this picture up here is of SN 2023 WRK, which is one of our publications from last year. And then these are Roger's in between observations, what is he doing? He's taking really cool astrophotography stacked images and colors them. How awesome is that? And this is of a transient in the sky, a local comet, a local asteroid blazing through their atmosphere. How cool is that? And so papers. So what is the impact of Kilonova Catcher? So the follow-up campaign of SN 2023 WRK started in the fall of 2023, and it lasted for a quarter of a year. And we published 2 papers on it. So out of 1,000 data points, 30% of those data points of this singular object was from amateur astronomers. So large-scale observatories, professional observatories, have a lot of bureaucracy, a lot of red tape. Amateur astronomers don't. So they can go outside, they can go to their local observatory where they have time, and they can start observing. They were so important to capture the spaces between where professional observatories could observe. 30%. And so this was a cool event. It helped us learn a lot about neutron star or neutron based stars like white dwarfs and neutron stars. And this SN 2023 WRK was a thermonuclear runaway of a carbon oxygen white dwarf exceeding the standard star car mass. To make this more consumable, the white dwarf was accreting mass from another object, and then it exploded. And so there's all this carbon, oxygen, and silicon left over that should have burned, but it didn't. And so we got to observe and understand what all that was going on. And so these were this was our light curve at the end, and you can see here that there was a list of a few different KNC names on the right side of this plot, and you can see the papers that came from this event. So 2, there was a note primarily for GRAMA. There was the science theory entirely with our Chinese partners with GRAMA, and we also have a paper from this year which details the follow-up event of a neutron star black hole merger that KNC also contributed to. The KNC astronomers that participated in this campaign for the neutron star black hole merger S2025-06DM, the SN 2023 WRK campaign, their names are on these papers as authors. They have, a DOI. They have a mark on the science community because of their contributions. So if you have a telescope, if you're interested in astrophotography, if you want to come to our webinars, if you want to check us out, I have a few links here. I also have this QR code that you can scan where you can put your email in and it'll send you a list of all of our links. It's not a sign up. It's not even a newsletter like thing. It's just so you can get the information if you're interested. You can email me. The email for KNC is on there. I'm the one who runs it, so you can contact me directly with your questions, and I'm happy to take questions now. So thank you for your time and for your attention. It's been wonderful.
Thanks, Christina. I'll start the questions off.
Mhm.
I know we do have a lot of astrophotographers in the group, but we also have people that have smart telescopes. Now, I know the Celestron Origin is like a 6-inch scope,
Yeah.
but the Unistellar is a 4th, I believe.
Mhm.
Are they usable?
It depends on the magnitudes they can reach. Most of the time, the answer is no. But if you can get to, 18, between 17 and 20, like you should be fine. For the Kilonova mergers, while powerful and not very bright because of the lack of diversity in baryonic matter, so they're a little bit harder to observe, but we do supernova and long GRB detection, which are going to be brighter, a little bit easier to observe and detect as well. So it might not be consistently able to follow the main science case with smaller telescopes, but you could still contribute.
Okay. Because I know on the older Unistellars, they were able to pick up on a star that went supernova in the Pinwheel Galaxy a couple of years ago.
Yeah.
So I don't know if that meets it. I'd have to go and look at the specs. I don't have them on me right now. Does anybody else here have questions? Sam, speak up loudly.
Okay. I guess kind of a follow-up question for the required equipment. Do you need a monochrome camera to take good data, or could you get away with a color camera with like a Bayer matrix?
Articulate again the different types of cameras you were.
So either like monochrome or color. I know
Oh,
monochrome
monochrome or color. Okay.
because I think most of the smart telescopes, if I'm not mistaken, use color sensors. So
Yeah, some of the
that
time
means I know
those
you
color
have
sensors can get in the way, actually. But that's a good question. I believe I believe monochrome is fine. It just depends again on the magnitude, but um I can ask the PI about uncolor. It depends what size is the telescope.
right. Yeah, I want to ask about that because with the color cameras, like unless you know like exactly the like the like I guess the profiles of like the color filters like versus wavelength, then it would be hard to like perform like photometry to
Yeah.
determine relative brightness of the target versus like the nearby stars.
Yeah. Yeah, I will follow up with that question because I don't want to give you a wrong answer or a misleading answer, and then I will email that to Jim.
All right, thank you. Do you have your hand up? Oh, okay. Anybody else have any questions?
Are most people using oscilloscopes or are they using like the SCTs?
Say that again?
Are most people using Rasa type scopes or are they using SCT type scopes?
SCTs.
Schmidt-Cassegrain, that's great.
Yeah, a riser is a fast imaging scope,
Yeah.
and then the Schmidt-Cassegrain. That's his question.
Uh, yeah, Schmidt-Cassegrain. I believe we use Schmidt-Cassegrain telescopes more. The fast operating ones are for smaller uh smaller what's it called? Duration imaging, and we tend to take long images to gather as much light as possible. There is a whole discussion about which one is better and which one is not. I believe it's a balance, but most of the time I hear them talking about SCTs.
Okay, yeah, the risers operated like an F2, so it's
Yeah.
like really fast. The scope one of our members had just bought for me is an 8-inch telescope, and he mounts the camera on the front, and that makes it an F2.
Yeah, because there are different modes, like for example, on larger telescopes like the SEDM, like the 2.1 meter in Kitt Peak, does have a fast readout mode, but it's not as lucrative for it does gather images for the on the it does gather quality images for the brighter parts of the event, but for the fainter parts, it is not as lucrative. Um, I'm not sure how it functions scaled down to an 8-inch level though. That's a good question.
Okay. Anybody else? I'm gonna ask another question myself. I know that we've talked about, picking up the images, stacking them, sending them in. But is there an opportunity for someone that may not have that capability to assist in like data crunching, data analysis?
Yes. So this summer, so April and May, the LIGO Virgo Kagra, the gravitational wave interferometers have been down. And we've taken that time to kind of reevaluate where Kilonova Catcher is not being utilized. And some of us, even the ones who have, backyard observatories, are in Chile or in places where there's a lot of weather. And so they're like, hey, we want to synthesize images. We want to help. We want to continue doing that. Is there any way we can? Unfortunately, currently, the photometry tool that we have called SCD Web um, is not user friendly. It does have quite a bit of a learning curve, even for the most proficient of astrophysicists. And so we are this summer adapting that tool. It's a pipeline to be serviceable to the amateur astronomers for those who cannot observe at the time or who want to synthesize their own images, or for people who do not have telescopes but want to contribute. And so that is something that is in development currently. It's being programmed, it's being tested, and that's what we're going to spend the summer doing. So hopefully it launches at the end of the summer.
Yeah, I'm going to ask a question from one of our members here. He probably will correct me, but you said spectrometer? Sorry, that's my Brooklyn. I can't pronounce it. Sam,
Spectroscopy?
one of our members, Sam, yeah, he made his own device here.
Oh, he has a spectrometer.
Yes.
Well, it's a spectrograph.
Okay.
Oh, a spectrograph. That's cool. That's awesome. That you are the second amateur astronomer I've heard who's done that. And I've actually talked
Douglas
to.
Smith by any chance?
Say that again?
Was the first one Douglas Smith that you've heard of?
No, he's an older gentleman here. I forgot his name. It's really cool though, because he's in his 70s and he just started his doctorate in astrophysics.
So maybe one day you, Douglas, or whoever the gentleman is, and Sam, we can do a side Zoom session to maybe
Yeah,
go over.
I'll get you. I'll let him know about you guys. Writing this down. I'll contact him about you guys. I see him every day at work.
Okay.
'Cause he was interested when I put a call out for Kilonova Catcher and for Grandma, for people to join. He was like, "Oh, I'd love to join. I have a spectrograph and everything." I'm like, "We don't have the tools for that at the moment." And I was already advocating for this when that occurred. And so this is even more of a case because now there's a greater population. So now I can go and say, "Hey, I have 3 people who are really interested in doing this for us, and we don't really have a strong spectroscopy side. We really should develop this."
All right.
So
Yeah,
thank you.
I'm gonna puff my chest out a little bit. Sam is our resident NASA intern for a couple of years. Did a lot of data crunching and extremely knowledgeable. And Armin, who just joined us recently, just as much as Sam is.
That's awesome. Congratulations, you two. I know that I have not let anybody in my family forget that I'm NASA funded since I got my NASA funding. So I know how that feels. Puffs out my chest too.
Okay. I thought I had another one, but it slipped right off my bald spot in my head. So I forgot what it was. Anybody else? Okay. Do you have any other programs that you work with other than Kilonova Catcher?
So Grandma's more on the professional side. If Sam, Autumn, the other individual you mentioned, if you guys are in STEM, if you guys are students looking for research, you can be a part of Grandma. We are always looking for new institutions, other institutions to collaborate with, because Grandma's made up of universities and professional observatories. So we can discuss that. I'm part of the core team of Grandma as well, so I'd be happy to start those discussions. But for amateur astronomers, no, I only facilitate Kilonova Catcher. However, I do have synergy with a few different projects. There's the GRB Burst Group, which is run by Amy Lien in the University of Florida. There is Dr. Robert Zelm. So Dr. Amy Lien in Florida. There's Dr. Robert Zelm who runs Exoplanet Watch, which also requires telescopes, and you can do it without a telescope as well. They study exoplanets. Currently, that is the primary 2 groups that I have synergy with at the moment. And then there's a few European-based amateur astronomy groups that our members are part of as well.
All right, cool.
Yeah.
Sam, if it's permissible, you okay to divulge what you guys are doing now?
Yeah, sure. We're both of us are in the same research group from NJIT. We're in the first year of our PhD. We're doing solar research.
Oh, there's a solar citizen science program that you guys could probably do research or facilitate or get involved in. I met her at the NASA Citizen Science Forum in November. Oh, what's her name? I actually have a whole list of contacts from that. Let's see if I will send Jim the name of the solar telescope group to see if you guys are interested in getting involved in that or just more people to network with, which is always important, especially in this day and age, and especially now to network with people in the field.
Okay, thank you. One more time, anyone else? Okay, Christina?
Yeah.
I'd like to thank you for joining us today. And I do owe you some contacts for other astronomy groups.
Yes.
The Adirondack Sky Center, I already mentioned it to Seth McGowan. The Mid-Hudson Astronomy Group. And I'll reach out to some of the other New Jersey groups as well.
Thank you. I plan to be back up there this summer to visit my family. So I will definitely ask if you'd like to go get some dinner or something.
Sure, I'm in Tom's River, just, let me know, and me and my wife would be more than willing, we'll invite you over, as long as you're not
Awesome.
allergic to cats.
Absolutely.
Okay.
Sounds wonderful. It was wonderful speaking for you guys. Wonderful meeting you all. Thank you so much for inviting me and thank you for the contacts. Sam, good luck. Wish you the best. And if you ever need any help with anything, if you ever just like to network, I'd be happy to facilitate any of that. Just have a conversation.
Okay, thank you. I appreciate it.
No problem.
All right, thank you.
Thank you.
And
I will send you all the information, my email, the presentation, everything.
okay, and I'll link you the video from when it becomes available.
Awesome. Thank you so much. Have a wonderful day.
All right, thank you.
Bye.
Well, bye.
Ben, get the lights.
No.